Alright, well let's look at some code for Quicksort, and this is not going to be a good implementation, so I'll call it bad Quicksort. I just didn't want you to come back to this slide and look at this and implement your homework assignment based on this one, because this doesn't do in-place partitioning like we want to do. Well, let's call our base case when we have one or fewer elements. In that case, we just returned. The array is already sorted if there are one or fewer elements. Next, we're going to choose a pivot, and let's say it can be anything in the entire array, and we will partition. So when we partition, we'll end up with the left side, the left bucket, and the right bucket. And again, those aren't already sorted. They need to be sorted, but at least they're all the elements less than and greater than the pivot, respectively. Then we're going to call Quicksort recursively on the left side to get the left side sorted, and then similarly on the right side. And then finally, we'll merge everything together. So the left side sorted, merge it with the actual pivot value, and then with the right side. So if you're wondering what this syntax is, this plus plus I'll just say is like sort of a concatenation of arrays or elements with arrays. Okay, well, what would be a good recurrence equation for Quicksort? Like I said, this isn't the version we'll implement, but it's close enough that we can start thinking about the recurrence equation. So write out a recurrence for this code. Well, I think a pretty reasonable one is to notice that all we're doing outside of Quicksort is a bunch of constant stuff, and then something that's probably linear, just based on how I described partition. So we'll have T of n for Quicksort is equal to big O of n for the stuff done outside of the recursive calls, plus, and you might be tempted to say 2 times T of n over 2. But that would be a mistake. It's not T of n over 2 because we're not guaranteed to end up with partitions that are even in size. So what we'll really end up with is T of x and T of n minus x minus 1. That's going to be a reasonable recurrence equation for this algorithm. So where does T of x come from? It's probably easier to start with the T of n minus x minus 1. Well, one of our calls is going to get, we're going to have all n elements. Well, we'll start with this one. We'll have all n elements, and x of those elements are going to go to the left recursive call, and n minus x will go to the right recursive call, plus another -1 here just to denote that the pivot value is actually being excluded from both the left call and the right call. We don't need to include it in those because it's already in its correct spot. Alright, well, how does partitioning work? The easy way is to do essentially exactly what we already discussed. We'll just copy all the elements into a new array. So we'll put the 8 at the end, the 2 at the front, the 5 at the end, the 1 at the front, and so on, and we'll just keep copying everything into a new array. This would be kind of like how merge sort worked. Inside of our merge routine, we had a left and a right, and we copied those into a combined array. So we had to allocate new space. There's nothing really inherently wrong with this in theory, but practically we can do a lot. We can be a lot more efficient if we don't require that extra memory allocation. So in fact, you can do an in-place merge sort like we're going to talk about here, but I didn't want to talk about it in the case of merge sort. We'll talk about it in the case of Quicksort. So let's talk about something called in-place partitioning. And for this discussion, let's assume that the pivot element for our partition procedure is always going to be in the first spot of the subarray, so the leftmost element. The leftmost element of our subarray. So what we're going to do, and just if that's causing you troubles, we can always just swap the element into that spot. Let's say we want to pick one at random, we can always just swap it into that first leftmost spot anyway. Alright, so our idea here is to gradually build up our buckets, our partitions, by scanning through the array. So at any given point in time, our snapshot looks like this. Our pivot's the leftmost element. To the right of it, we have all the elements that will eventually go to the left of it, so the smaller than. To the right of that, we'll have the greater than, and then we'll have all the unpartitioned elements to the right of that. Okay, so this is how we will operate our in-place partitioning procedure. We'll have an index that is always 1 to the right of the smaller than partition, and we'll have an index that's always 1 to the right of the larger than partition. Why it's 1 to the right and not like the first element or something will make sense as we start to step through the code. Okay, so here is our array. The question I have for you is, how should we initialize I and j? So at this point, everything is unpartitioned. So what's a good initial value for I and j? So that's 1 to the right of the smaller than partition and 1 to the right of the larger than partition. Well, we don't have a smaller than partition or a larger than partition, but you can picture them sort of being right in here. They're always between the pivot and the unpartitioned space. So if we go 1 to the right of that, we're going to initialize I and j just to the first element to the right of the pivot. And then we have to ask ourselves, here's our first element we're looking at. It's our first unpartitioned element. To which partition does 8 belong? Well, 8 belongs to the greater than partition, the larger than partition. And how do I put it there? Well, if I look at my indices here, if you notice, I always points to the first element in the larger than partition, so I is already correct. And j always points 1 to the right of the larger than partition. So how do I get 8 to its correct spot? I just need to move j 1 to the right, so increment j. Okay, so now we have this as our unpartitioned space. To which partition does 2 belong? 2 would belong to the less than partition. How do I put it there? Well, again, I should always point to the first element of the greater than partition, and j should always point to the first unpartitioned element, essentially. So what do I do with j is pretty simple. I always will increment j. But how do I increment I? Well, if I increment I and have it point at 2, that would mean that 8 is to the left of 2, which would put it in the less than partition. So I can't just get away with incrementing I. I have to do something else. And in this case, I'm going to swap the 2 and the 8. So when I swap them, now I can just increment both of my variables. So let's take a look at our state now. I is 1 to the left, or sorry, 1 to the right of the less than partition. Well, this is our only element in the left than partition, so that's correct. J is 1 to the right of the larger than partition. There's only one element in the larger than partition, so I and j are both correct. Alright, so to which partition does 5 belong? 5 is greater than 3, so it belongs to the greater than partition. How do I put it there? Again, anytime I'm putting something in the larger than partition, all I have to do is increment j. And whenever I'm needing to put something in the less than partition, like 1, I always swap with the value currently at I. So this is why I is always 1 to the right of the smaller than partition, because the item that's there is more than likely the leftmost element in the greater than partition. So it's the place where we need to wedge in the next smaller value and then increase the size of the smaller than or less than partition. So I'm always going to do a swap when I see something that goes in the smaller than partition. And then I'll increment both I and j. And then for these final 3 values, all I have to do is increment j. So now j is at the very end. And what's the final thing that I need to do? Well, I need to put my 3 in the correct spot. So how do I put 3 in the correct spot? Well, to put the pivot in the correct spot, I'm always going to take out this value here, because I want all of the values in this block to be to the left of the pivot, and I want all of the values in this block to be to the right of it. So the easiest way to do that is just to swap the rightmost element in the smaller than partition with the pivot itself. So I'll swap those 2 values. Now 3 is in the correct spot, and the other elements are bucketed correctly.